Hi, in this video, we are going to be implementing the expression that we found in part two um, of this 6-part series. So this is part 3. We are going to be implementing that expression in Python. And we also want to show the transition from stable to unstable results of discretization. So one thing that we need to know is that in the situation that we've already described, we are going to say that the bar is 50 meters in length. The thermal diffusivity is just going to be 1. And then we're going to use a spatial step size of 1 meter. Okay, so the first thing that we're going to do is we're going to import numpy as usual. Oh. And then we said that the thermal diffusivity was just 1, so we'll call that alpha. And we want to specify how many time and length increments we're going to use. And we said that we want, we said that we wanted to use a spatial step size of 1 meter, and the length of the bar is 50 meters. So we'll do 50 increments of 1 meter. And then we'll just use an arbitrary value for the time increment for now. So we'll just say it's 100. And then we want to, so 50 increments of length, that's our NX, our number of length increments. 100 increments of time, that's NT, that's our number of time increments. And then our, the length of each increment is just going to be 1. And we can choose a time increment length. I'm going to say 0.1. And then we can also give value to R, because in the last video, we said that we just wanted to set our, give it basically like the thermal diffusivity and the multiplied by the change in time divided by the change in position squared, that part of the expression. We just called that R, so we can go ahead and give that a value as well. And so the thermal diffusivity is alpha. Then our change in time is dt. And our change in position squared. And I'll go ahead and pull up that derivation just for a reminder. Okay, so now I have the derivation of the expression that we found in part 2 pulled up. And again, our R value is just down here. It's equal to alpha delta t over delta x squared. And this is our full equation. So pull back up the code. And then we want to give an initial temperature value to each segment of the bar. And we can do this using an array. So and we'll just give every segment of the bar the same initial temperature. So we're doing this for NX since it's each physical segment of the bar. And we'll just say 20 Celsius. Yeah. So let's see. Yeah, so the shape is just NX since that's the number of segments, and then, yeah, 20 Celsius for each one. So now we want to start changing it up. So we will start by heating either end of the bar. So we can do this by assigning a temperature value to each end. So the left-hand side is going to be indexed at 0. And we can just say that it's 50 Celsius. Right. And for the right-hand side, it's indexed at -1. And again, these like heated raised temperatures are just arbitrary values, but we can choose whatever we want. I'll pick 80 for this side. And then we can check that really quick. Yeah, so we have hopefully 50 values here, all 20 Celsius, but the leftmost one is 50 Celsius and the rightmost one is 80 Celsius. Okay, so let's go ahead and plot this and see what it looks like. So we'll have to import Plotly. Okay. So we're going to end up needing both of these imports to graph everything that we want to graph in this video. And so let's go ahead and start on that. So we'll call it just figure as always. And for now, we only need one row, one column. And our X values are just going to be the number of the position increments. So NX or multiplied by their length. Because it is our position along the bar, and then our Y values are obviously going to be the temperature. So X, we can use the arrange of NX, again, multiplied by the length of each increment, dx. So now we can just use that as our X. So we can just say X equals X for the figure. So fig dot add trace. We want to do a scatter plot. So X equals X, and then Y equals the temperature. Temperature values. So Y equals T. And then we'll call it initial, since this isn't our like final result. Oh, I didn't. Did I spell range wrong? I think there might only be one R. Yeah. Okay. Because it's a range, not like a range. Okay. So this looks good. This is what we want. So across the bar, we can see that it stays at 20 Celsius until like the right hand side we have 80 and then the left hand side we have 50. So now we want to calculate the temperatures of all the internal nodes using our expression that we found in part 2. So now that's going to come in handy. If we have set the external node temperatures to 50 and 80 degrees, then we can use the expression to calculate it using a for loop in the code. So so our arguments yeah, so it's going to be the change in time, the number of time increments, and then we'll have to pull up the thing again. Okay, so now I have it pulled up, and we're going to use this to write out that expression for this for loop. So basically we really just need to enter it in, but the trickiest part about this is the indexing. But we know that the what we're trying to find and what is the leftmost variable on this expression is the temperature of the internal nodes, which with the indexing is just going to be from 1 to -1 since the indexing starts at 0. So we have that, and that's equal to that once again, plus r times what is in the parentheses. And that first value in the parentheses is the previous temperature. So it's going to be like all of the temperatures shifted to the right. Yeah, because it's 2 to the end. So that's just going to be 2 colon and then minus 2 times all of those internal ones once again, plus all of the temperatures shifted to the right. So that's going to be 0 to -2. Okay. No, that would be all of the temperature shifted to the left. Yeah, and this value is all the temperature shifted to the right. Okay, yes. Okay, so now we want to go ahead and graph that, which we can do. We're gonna do a scatter plot. Ooh, did we already? Yeah, we already put in everything. Well, we can just copy and paste this actually from up here. Okay, and then we'll just delete this name thing. Oh, and we can get rid of that. We need to show it again. I'm going to. Oh, I know it's wrong. had to basically come back in, and I filmed this in one take the first time, and when I went back and looked at the video, it like showed a different screen for some reason, like a different page that I had pulled up. So this also needs to be 0.1. This is what we originally had. I'm like splicing these clips together, so sorry about that. Okay, yes. So this is what we want. So ignore that basically because it did not happen in this video technically. That's the reason why it was stalling like that. But this is what we want for that expression that we found in part 2. So now we can use the modulo function and an if then statement for in the for loop to increase our number of time increments, but to continue to only plot every second, because basically what the modulo function does is it finds the remainder of something. So if we let's see, we add it in here. If we make if we divide it by 100 and the remainder is 0, then we will continue to only plot every second if we change the number of time increments to 1,000, which is what I had previously from messing up the first video. But yeah, so that's what we want to do. And then this needs to be indented. Okay. Yes, so now we are done, and this is beautiful. This is what we want. But the last thing that I want to point out before we move on to part 4 are the instabilities that we mentioned at the beginning of the video, which we can see if we play around with the number of time or the length of the time increments. So if we set this to like 0.6, it gets really wonky. And this looks totally different from the graph that we initially had. But if we do something a little bit closer, it's easier to see. So 0.5 still looks similar, but if we do like 0.55, no, 0.55 looks like 0.6. If we do 0.51, you can start to see them like these other pieces coming in. 0.505, and they're really starting to come in. 503, and yeah, so this is incorrect, and this happens because basically the way that we went about doing the finite differencing is unstable for certain values of R, and we can fix this, and we will do that in a later part of this series using the Crank-Nicolson finite differencing scheme. So yeah, I think that's part 5 or 6. So eventually we will be able to fix this, but if we switch it back, it looks good for now. So thank you for watching this video.